Hi everyone, good afternoon and welcome back to the fourth lecture of the analytical chemistry series. This is a continuation of the first lecture, because I didn't manage to cover everything I wanted to. So I'll discuss error in qualitative tests before moving on to biological variation, then moving on to a biochemistry reminder, and then finally an introduction into the following lectures, all of which are each about a particular analytical method. Here are the learning objectives. We're going to describe and discuss error in qualitative tests. We're going to understand biological variation and how it may be calculated. We're going to understand how this variation may relate to reference intervals. And remind ourselves of some of the common molecules and their molecular features. Remind ourselves why pH is important and some common calculations, and then describe the general purpose of analytical methods. So first of all, thinking about qualitative tests, where the results give you a binary output, yes or no. Urine pregnancy is a good example. Urine pregnancy testing, is a good example. Urine reaches the test line, and if HCG is present, reacts with antibodies to produce a color change. The second control line is present to prove the urine has reached this. The beta HCG needs to be a concentration of about 20 to 25 million international units per mil, so it can easily miss early pregnancy when the concentrations are lower. Thus, it still uses a cutoff, not just a is it there or not. Fit testing is an even better example. A cutoff for concern is defined at 10 micrograms per gram of feces, and less is defined as normal. This means that it may be normal to have a tiny amount of hemoglobin in your feces. And so although the test is quantitative and can actually give you a level, the actual levels do not hold so much meaning. So this is a theoretical qualitative test. Choosing a cutoff of 117 would helpfully distinguish our sick population here in red from our healthy population here in blue. This would be a perfect test. We'd identify everyone who is healthy and everyone who is sick. If the overlap between the sick population and the healthy population is complete, the test would be useless. It does not distinguish healthy from unhealthy. And even if you used a cutoff, let's say here of 50, about half your healthy population would have a positive test result, even though you would pick up all your patients with the disease. Now, this is a more realistic situation. Although you've designed a test to pick up the sick population, there is still some overlap where some patients will be well or do not have the disease in question, depending on where you actually place the cutoff for your test. The error in the test comes from this overlap, falsely giving some people without the disease a positive result and falsely giving people who are diseased a negative result. Of note here, I will also point out that the population distribution of analytes is not always normally distributed, as I've suggested here. You may have some form of skewed distribution. And this is different to the repetitive sampling to find the mean of the distribution that I discussed in the first lecture. Repetitive sampling to give an estimate of the mean will always be normally distributed because of the central limit theorem. This is different to population sampling. Now, 2x2 tables are the classical way of describing the outcomes from these tests that we're putting in place. Like in the first lecture, you require a reference method to define if a patient is sick or healthy. Now, this may be a reference analytical method, or it may be a clinical feature. For example, colonoscopy will be the gold standard for colorectal cancer diagnosis, but you use fecal immunochemical testing. And Western blot or RNA testing may be used as a definitive method in HIV infection, rather than using an ELISA for antibodies against HIV, which would be your test here. So this is an example where the prevalence of a particular condition is 40% and 100 people are tested. Knowing who is diseased versus who is healthy with our reference method or our clinical methods means we can see how our test stacks up. Here, 36 patients with the disease had a positive test, and 4 patients with the disease had a negative test. 12 healthy patients had a positive test, and 48 healthy patients had a negative test. So our first definition is sensitivity. And all this is how well your test can pick up the disease. So we can see that 36 patients with the disease had a positive test and 4 patients with the disease had a negative test. So seeing how well it can pick it up is 36 divided by 36 plus 4, 40, times by 100 to give a percentage. Our sensitivity for this test is 90%. Specificity is about ensuring that healthy persons or persons without the disease do not receive a positive result. Here you can see that 48 healthy patients had a negative test, but 12 had a positive. So the specificity is 48 divided by the 48 plus 12 gives you a specificity of 80%. And we can see this here on our original diagram. The sensitivity, if this is the particular cutoff for the test, the sensitivity is this area here for the sick population, the proportion of the sick population that you're picking up with the test. The specificity is from the healthy population, the blue population here, is all of this area here. Now, both of these can be combined together into diagnostic accuracy, which is effectively the proportion of correct results. So 36 patients with the disease are correctly found to have a positive test, and 48 healthy patients correctly given a negative test. So the diagnostic accuracy is 36 plus 48 divided by the number of tests done. That's all of these, which is 100, multiplied by 100 as for a percentage, and your diagnostic accuracy is 84%. Now, PPV is the positive predictive value. This is much more individual-centric than the focus on the population that you get with sensitivity and specificity. It says that if you are in receipt of a positive test, how likely are you to have the condition? So in this case, if you have a positive test, 36 of those patients will be diseased and 12 will be healthy. The positive predictive value is 36 divided by 36 plus 12. Multiplied by 100, you get a positive predictive value of 75%. Negative predictive value is the converse. If you have a negative test, how likely is it that you are healthy and you do not have the disease? This would be 48 divided by 48 plus 4, multiplied by 100, gives you a negative predictive value of 92.3%. Remember that for some tests, such as the fecal immunochemical testing, you may be able to change your cutoff for when you're concerned or when you send people for further investigation. And for other ones, you may be unable, like the urine pregnancy, unless you actually change your analytical test to make it more or less able to pick up the analytes. Now, even with a fixed cutoff, there's an issue with defining specificity and sensitivity for a population for a particular disease. If I fix the sensitivity at 90% and the specificity at 80% in both of these examples, but alter the prevalence of the condition that we're testing for, and the absolute numbers that you get here change significantly. And you can see here that suddenly you're much more likely to be healthy than diseased if you receive a positive test in comparison to our first example here. And all I've done is alter the prevalence, the sensitivity and specificity have stayed the same. You can see that this is picked up well in the positive predictive value, which has dropped to 33.3% from 75% here. Now, this has significant implications on the utility of the test in a clinical environment. How many well people will undergo further, possibly invasive investigations? Can the service handle such a high throughput for such a small proportion of disease? And this may be a more realistic example. A cancer screening tool with a sensitivity of 90% and a specificity of 68%. Those numbers sound fantastic, where cancer is of low prevalence. If we look at the numbers here, you can see that although it picks up the patients who are diseased reasonably well, it also picks up a vast number of the healthy population. And so even with these good numbers, your positive predictive value is actually sitting around 0.28%. So the reality is that this test may not be helpful, may not be possible to roll it out, and that's something that needs to be considered when people report sensitivity and specificity, but fail to report prevalence of a condition, and therefore the positive predictive value of a test. Now, deciding on a cutoff for your test may be dependent on the ability of the test, or it can be something you can change. The cutoff may be criteria for referral or for further investigation, or it may even be diagnostic criteria. Now, if you're able to change the cutoff, so actually change where the cutoff value comes, then you can plot the changing sensitivity and specificity for each cutoff on a plot called a receiver operating characteristic curve. Now, here's an example using FIT testing for a population of people with low-risk symptoms of colorectal cancer. Sensitivity is plotted on the y-axis, and 1 minus specificity is plotted on the x-axis. Sometimes on the y-axis, this is called the event detection rate, and on the x-axis, sometimes called the false alarm rate. Now, you can see the sensitivity is this part of the red-pink population here, this proportion compared to the overall proportion, using this as a cutoff. And the specificity, 1 minus specificity, sorry, is this area of the blue curve that comes after the cutoff. And this is suggesting that you can alter the cutoff this way or this way. From left to right, so going towards the left, each point shows a different cutoff, and this is an increasing threshold as you move towards the zero. As you move towards the left of the graph, it's a higher cutoff. As you can see, the sensitivity drops when you increase the cutoff, and as you move towards the right, that's a lower cutoff, where you can pick up all the sick patients, but you start to lose your specificity. Now, if the line is at unity, which is this green line here, which is just a 1-to-1 ratio, so 1 minus specificity of 0.25 and a sensitivity of 0.25, this suggests that the test is completely meaningless and does not distinguish your sick population from your healthy population. Therefore, the area under the curve that will be plotted by best fit through all of your points here, the area under the curve that is obtained here will give you an idea of how good your test actually stacks up. And 1 would obviously be the best, the area under the curve being 1, and 0.5, which is the area under this line here at unity, being an awful test. So you'll get a value of somewhere in between 1 and 0.5. But aside from using the area under the curve just to see how good your test is, you can also use the curve to choose the best cutoff, to say, well, this is the best sensitivity, which gives me an acceptable 1 minus specificity. And this will be test specific. What do you need the test for? Are you happy with lots of false positives? Do you need the sensitivity to be nearly 1? So far, we've discussed measuring error in qualitative tests, the problems with specificity and sensitivity and the requirement to consider prevalence, the use of ROC curves and how to read them, and choice of diagnostic cutoff. The biological variation, the observed differences both within and between individuals. We know that individuals differ, whether that be height or the concentration of ALT in their bloodstream. The difference may be expected from differing physiology, metabolism, genetics, or it may signify disease. The range of values which individuals may take on could be normally distributed, or it cannot be. And if not, it tends to show a positive or negative skew, whereby results are clustered at low in the case of positive skew, or high values in the case of negative skew. And again, we're talking about population distributions. That's different from population sampling multiple times to find the mean value, which will give us a normal distribution if we do this a number of times. But the population distribution of the values is not necessarily normal, although it may be in the case of height, for example, may look something like this, which looks very normally distributed. So biological variation has two components. The first is described here as CVI, which is the intra-individual variation. This suggests that every individual has a homeostatic set point, an average value that a particular analyte is in their body, and it fluctuates around that value in health. A good example is creatinine, which may fluctuate by a few micromoles per litre throughout the day in health. Those fluctuations dependent largely on fluid intake and activity, but the average value is determined by muscle mass and renal clearance. CVG, but between individual variation. This is the difference between all the different individuals' homeostatic set points, the average values that their analytes or physiology is set at. We know that people's creatinine set points are distinguished by muscle mass and renal clearance, which of course differ between people, and that gives rise to this between individual variation. Now, CV, or coefficient of variance, is used here as percentages so that we can use numbers that are equivalent between different concentrations and things that mean something between different analytes. And remember that this is equal to the standard deviation divided by the mean. When we want to look at the total variation that we may expect to see for an analyte on a particular analytical platform across the population, if we just test a number of people in the population once, then we may want to add all three of these terms. The CVA is analytical variation, which is the imprecision that we've spoken about in the last 3 lectures. And this you can measure from doing your verifications. So to put everything together into a total variation, you get this equation that looks reasonably complicated, but all you're doing is squaring each of the individual components of the variation and then square rooting that number to get your total variance. And the reason for this is because standard deviations cannot be added, but variances can, and variance is the square of the standard deviation. And I'm just going to describe this process on a graph to make it a little bit clearer to understand. But here, this orange distribution is the analytical imprecision for a particular analyte. The green is the within individual variation, the intra-individual variation for a particular analyte. The blue being the between individual, so all the differences in the population between the homeostatic set points for a particular analyte. And then if you actually add all of these variances together, you can produce an overall total variation that you can see in the red line that will describe what the population would look like if you went along and took multiple value, or took one value from each person in the population, and you would get something that looks like this, because each individual value would be something that looks similar to the average. You would be basically selecting people from who may have variation in the population sitting somewhere on this blue curve, and then their day-to-day variation is described by this green curve, and then the analytical imprecision described by the yellow curve could all interact to produce people's results somewhere over here, somewhere here, if that makes sense. Again, this is not the total variation, is not the distribution of values you'd expect for an individual, it's the distribution of values you'd expect for a population. I previously pointed out that the distribution for some analytes may be skewed, sometimes positively skewed, like ALT here. And you may be asking, how do you calculate a standard deviation and a coefficient of variation for something like ALT? Now, in these situations, you can try and transform the data into something that looks more normally distributed, let's say by logging the ALT values. And then you can use this distribution to provide an estimate of your standard deviation, and then back transform, so back log back here to give you a coefficient of variation. And work has actually gone into trying to define these components, CVI and CVG, so within individual and between individual biological variation, in a very systematic way. And the European Federation of Laboratory Medicine have defined how we study, or how we should be studying these components, and amassed a large amount of data for multiple analytes. And the website is included here. It's definitely worth having a look. It's called biologicalvariation.eu. And this is an example here of ALT. And the top bit here is the within subject variation. And the bottom one here is between subject variation. For within subject, the data will involve repeated measurements for the same individual over a short period of time. And the between individual will require the average, or what we'd say is the homeostatic set point of each individual in each individual, and comparing that value with other members in the population, so different people. There's also a reference change calculator that's worth looking at. This uses an estimate for intra-individual variation or within subject CV, and the analytical variation of your method, which you input yourself. And this can be found on your verification of the analytical method. And so you get something that looks, like this when you use the reference change value calculator. So it will tell you what the within subject variance estimate or coefficient of variance estimate is. You'll put in your analytical imprecision yourself, and you'll put in a probability. I want to know with 95% certainty that a value that changes between if a patient has two of the same tests, is there actually a significant difference between the first test and the second test, or could it be accounted for by this within subject variation and the analytical imprecision? And you get something that looks like this. It tells you what numbers they've used to the within individual variation and the analytical variation that you've inputted yourself. And it says that you're 95% certain that if there's an increase from the first measurement of 41.5% to the second measurement, or a decrease of 29.3% of the first measurement to a second measurement, that's when you're 95% certain that there's a difference between those two values. And I'll just go back. And it's really useful, but it's important to take it in context. The clinical situation may not tolerate a 95% certainty of a change, which may be pathological. For example, rising urea with a small rise in creatinine may still be suggesting dehydration in a patient, even if the change is not greater than would be expected from normal variation and analytical variation. So you may not have met the reference change threshold, but you would still have to be doing something about it, because clinically, whatever you're seeing is still relevant. So it's important that this is still taken into context. But reference change values are rarely reported clinically, and people can decide that there's a difference between two values without there really necessarily being one. And reference intervals follow on really well from this. Reference intervals tend to be given with results, and they're typically healthy population reference intervals, defined by the range of 95% of the healthy population. They can be useful for people who've not had blood tests before, but as mentioned previously, they can hide significant changes that may be pathological. Consider this. If the blue curve shows the individual variation for a particular person, for a particular analyte, varying around this central homeostatic point, which would be the mean of this, and the general population variance is given by this red curve, then changes outside this individual set point, let's say they have a value here, may not be outside the population reference range, but would be abnormal for this patient, single patient, who's described in blue here. And a way of describing how important this effect is the index of individuality. It's the ratio of within subject variation compared to the ratio of between subject variation. If it's close to 1, then these two curves are very similar, and population-based reference intervals can be applied quite easily. Serum bicarbonate is a very good example of this. If the index of individuality is small, much less than 1, then people's values sit around a tight set point, but the population range is much larger. This is the case for lots of analytes and means that reference ranges are less useful. Creatinine is a great example, and we use a rise of 26 to define AKI with creatinine, even if that does not leave the reference range. This ratio is less likely to be greater than 1, but can be, and I think adrenaline is a good example of an analyte where this ratio might be greater than 1. So far, we've discussed biological variation and its components, how to separate out these components, and considering the use of reference intervals and the problems with them. I'm going to move on to the biochemistry reminder now. So again, this is going to be quite a quick overview, and if it seems completely new, then it may be worth getting in touch, and I can suggest some more places to read some of these concepts in greater depth. So first of all, I'd just like to mention the different types of molecules and remembering groups and how that defines some molecules. So hopefully these sorts of diagrams are familiar to you. So first of all, this is a carboxylic acid group. So R can be a hydrogen or it can be a hydrocarbon chain. So a chain of carbon atoms with hydrogens off. This here is a ketone, which is double bond oxygen to a carbon with either hydrogens or hydrocarbon chains attached. The third here is an alcohol. This has to be a hydrocarbon chain. If it's just a hydrogen, it would be water. This here is an ester. This will be a hydrocarbon chain. This can be a hydrogen atom or a hydrocarbon chain. And this here is an ether, 2 hydrocarbon chains separated by an oxygen atom. Now, you may recall that oxygen is very electronegative, which means that it pulls electrons towards itself. And that gives these molecules particular properties. The partial negative charge that oxygen gains from pulling electrons towards itself alter the distribution of electrons in this molecule, so much so to the fact that the electrons sitting in the bond between the hydrogen and the oxygen here are very much closer to the oxygen. And this means that this hydrogen and a positively charged hydrogen is just simply a proton, the bond here is very easily broken, and the hydrogen ion is easily lost in solution. And that's why these molecules are described as carboxylic acids, because they readily lose this hydrogen ion, which is a proton, in solution. Now, this is compared to alcohols, where they do not have this carbon with a double bond oxygen group here. And that means that although the oxygen is still electronegative and has a slight negative charge on it, but it pulls the electrons from pulls the electron from the hydrogen slightly closer to itself, giving you a slightly positive charge on the hydrogen, which is what allows alcohols to participate in hydrogen bonding. The electrons aren't pulled so far away that this bond is so easily broken, and for that reason, alcohols do not readily lose a proton in solution, and they're not described as acids. The same thing with this carbon the oxygen double bond here in an ester means that the electrons are pulled away from are pulled towards this oxygen atom, again giving a slight positive charge here at the carbon, and for this reason this bond here is very easily or more easily broken, and that's why ester linkages can be hydrolyzed or often used in molecules where they can be hydrolyzed. And I wanted to move on and just show you the molecular structure of 3-beta hydroxybutyrate, which is classically a ketone body. But you'll notice with a carbon double bonded oxygen, with an oxygen here and an H plus that would have been lost from the molecule, that 3-beta hydroxybutyrate contains a carboxylic acid group and is therefore a carboxylic acid, not a ketone. Now, having just said that as well, despite the term ketoacidosis and lactic acidosis, neither of those molecules are formed as an acid with an H plus in metabolism, just as the anion without an H plus. But a 3-beta hydroxybutyric acid is a carboxylic has a carboxylic acid group, not a ketone group. Now, pH defines the behavior of molecules in solution. And to start by just quickly talking about water, obviously it's very abundant on Earth. It's got very unique properties, which means that it's the medium within which chemical reactions of life happen. These unique properties are that it's a near universal solvent. So what I mean by this is it can dissolve a wide variety of substances, carrying nutrients, waste products, and chemical signals in the body. It's got polarity in the same way. You've got a slight negative charge on the oxygen because it's very electronegative, which gives the hydrogen atoms a slight positive charge, which means that water can participate in hydrogen bonding. But it also means it can dissolve positively and negatively charged molecules, including acids and bases. Many biochemical reactions occur in aqueous solutions. The dissolved molecules are more freely able to move and therefore able to participate in reactions. But water also has an active role, hydrolysis, dehydration reactions. And you can see that the role that water plays by knowing that it's required for ATP hydrolysis to ADP, which releases energy. A high heat capacity, which means when you apply heat, it doesn't change temperature very much. We'll talk about acids and bases, and obviously it's also liquid at ambient temperature, which is perfect for us. So remember that the H plus ion, the hydrogen ion, is simply a proton, which is a positively charged atom with no electrons or neutrons. It's just a proton. And typically uncharged hydrogen is 1 proton and 1 electron, which balances the charge. And the Arrhenius definition of acids are compounds that increase the H plus concentration in water in aqueous environment. And in fact, H plus does not sit alone and instead immediately bonds with water, H2O, to produce H3O plus. Now, if we look here, what I actually meant to write here was 2H2O goes in the forward direction and in the backward direction to H3O plus and OH minus. This makes water amphiprotic, the ability to either lose a proton or accept one, and it can react with itself. Now, this above equation is very important, and it's a simple equilibrium one. So it can proceed in the forward direction and in the backward direction. Pure liquid water at 25 degrees is nearly all formed of H2O and only tiny amounts of H3O plus and OH minus. And you can see with the reaction stoichiometry there that your H3O plus or H plus concentration is going to be equal to your OH minus concentration. And at 25 degrees, liquid water has this much H plus or H3O plus and OH minus, 1 × 10⁻⁷ molar, which is moles per liter. Now, the pH scale was defined to describe the concentrations of H3O plus or H plus in really simple terms. And it's the minus log of the H plus or H3O plus concentration. So if we put in this concentration here, we get a pH of 7. We know that the pH of pure water is 7, and this is all due to water reacting with itself to produce a concentration of H plus in this range. Now, the Bronsted-Lowry theory of acid-base suggests that an acid is something which donates an H plus, and a base is something which accepts an H plus. So in terms of our above equation, if a molecule donates an H plus to water, we know in equilibrium that this will rise this concentration here, and that means that more of this will react with the OH minus, pushing the reaction back towards the left, towards water. And if the molecule accepts an H plus, it's a base, then that will reduce the concentration of this, and this reaction will be pushed towards the right. So water does act as a buffer. It's not a very good one because OH minus and H3O plus are at such small concentrations, but water does act as a buffer. And we don't tend to consider this reaction unless the amount of acid or alkali you're adding is smaller than this sort of concentration. Now, if we think about acids and bases, we'll talk about strong versus weak acids. And the difference between the two is just in the way that the reaction can proceed. Strong acids, completely dissociate and ionize in aqueous solution. So XH goes to X minus plus H plus, and all of it does that. So there's no backwards reaction. For example, hydrochloric acid, all will become H plus, which goes immediately and becomes H3O plus and Cl minus. Weak acids do not completely ionize, meaning that you have products on both sides of the equation. XH goes backwards and forwards to X minus and H plus. And this is a simple equilibrium. So increasing the proportion of either of the products will push the reaction back towards the left. Now, does the body produce strong acids? Well, it's sensible for the body not to produce strong acids because strong acids tend to dominate the pH of a solution because you release the acid. And HCl is an example in the body of a strong acid that's produced, which is produced in the stomach and used for a very particular purpose. But strong acids aren't commonly produced in the body in cells. By sticking with weak acids, we can regulate the pH better because altering the concentration of H plus will alter this equilibrium. So this is the equilibrium constant for a particular acid that is a weak acid, so the reaction can progress in this direction or progress backwards in this direction. And all this says is the concentration of the products divided by the concentration of the reactant is going to be a particular, is going to be sitting at equilibrium. If you were to increase the concentration of the H plus, let's say, it would push the equilibrium back towards the left, increasing the concentration of HA, reducing the concentration of A minus and H plus, and this overall stoichiometry would be maintained. And Ka, because it's the equilibrium constant for an acid. So the Ka is, yeah. However, in the body, there are multiple weak acids, all of which interact to lead to a pH. We've seen that a rising H plus should push the equilibrium towards the unionized molecule. Thus, the pH of a solution that the weak acid enters can also determine how it will behave. And by that, I mean whether it stays on the left side or the right side of the equilibrium. If you place a weak acid HA into a solution which has a very, very high H plus concentration, then the equation will sit, or the direction of the equilibrium will sit further on the left to try and maintain the equilibrium in a ratio that is defined by the particular acid. Now, our Ka equation can be rearranged to describe some of these features more meaningfully. So if we take the H plus off the top and just do H plus times A minus over HA, and then we take the minus log of all of these components and call the minus log of the Ka, the pKa. The minus log of H plus obviously becomes pH. And we know that when you've got a multiplicative term inside a log equation, you can just add, you can separate it out and just add the terms. The minus log H plus plus minus log A minus over HA. And then rearranging this equations, you've got pH on one side and pKa and your log A minus over HA on the other side, gives you this very familiar equation. So the pH of a particular solution can be linked to the pKa and the ratio of the ionized acid molecule to the unionized HA. And this is really important in a buffered solution, one that doesn't change pH much, as it means that we can describe the behavior of the acid in the solution, because we will know what the ratio between the ionized acid and the HA is. For example, the pKa of ethanol is 15.9, and we know that the pH of the body sits around 7.35. Therefore, we can work out the ratio of A- over HA by reverse logging, by subtracting and reverse logging this value. A- over HA in this example comes to a very, very, very tiny ratio. And this means that most of ethanol at physiological pH sits as HA. So the hydrogen atom is not lost from the molecule, it's not separated out from the molecule. If we were to bring the pH of a solution up to about 14, so a very alkaline solution, and pH of 14 is the highest you can go in water, then you would find that this ratio changes and you'll have more O-. So altering the pH of the solution you put ethanol in will mean that more H+ may be released from the molecule, more anion released. In general, the rule when interpreting this equation is that if the pH is below the pKa, then more will be unionized, so release less A- and H+. And if it's above the pKa, then more will be ionized, so release more H+, release more A-. The pKa of 3-beta-hydroxybutyric acid is 4.4, so it sits mainly in anionic form in the bloodstream. So it won't take on and take up an H+ atom. That bond will not reform in hydroxybutyric acid. And just to go back, actually, I mentioned before that the electronegative oxygen atom means a slight positive charge on the hydrogen atom, and it's not enough to actually break this bond very easily, which is why it doesn't easily break in solution, hence the very high pKa. And obviously at much more alkaline pHs, that will allow this bond to break more easily. Now, the body maintains a narrow pH to continue cellular functions. It would not be good for the production of acids to vastly change the pH of the body due to the effects on molecular structure and function. The most important buffer system to do this is the carbonic acid bicarbonate buffer system. And as with all buffer systems, you need an adequate supply of anion and unionized acid. In this case, the anion is bicarbonate, and the unionized acid is CO2, which reacts in solution to H2CO3. So this is your unionized acid. And the body can regulate each of these separately in health. We know the body can regulate the partial pressure of CO2 in the bloodstream, and we know that the body via the kidneys can alter the concentration of bicarbonate in the bloodstream. To maintain this ratio, the body will always act to maintain this ratio, and that allows us to maintain a stable pH. And we can see this with the equation here, that the pH is equal to the pKa, and it's 6.35 for this molecule H2CO3. And if we log the bicarbonate concentration over the H2CO3, the partial pressure of CO2 multiplied by 0.231, if this is measured in kilopascals, will give you the concentration of H2CO3. This is the solubility coefficient. So we can see that by altering both of these allows us to control the pH in solution. And this is how we describe things like respiratory acidosis, respiratory alkalosis, metabolic acidosis, metabolic alkalosis, by what the body's doing to try and maintain this ratio, and say that it's compensated if the pH is held normal, or decompensated if the pH isn't held normal. A quick final note on light, or I should probably say electromagnetic radiation, of which visible light is one part. The basic concept is a photon that can carry energy that can be transferred to molecules. In some situations, it can be described as a wave and particle in others. The shorter the wavelength, the more energy that can be transferred. Thus, ionizing radiation to the right of the electromagnetic spectrum is damaging. It can be damaging to humans because it has the ability to knock electrons from atoms because it can give them a higher amount of energy. We know that light carries energy because aside from requiring energy to make our rod and cone cells in our retinas via electrical impulses, allowing us to see visible light, we also feel warmth from the sun or a light bulb. And the equation that relates the wavelength of light to the energy of a photon, E, is hc over lambda. Lambda is the wavelength of the light, and hc are both constants, the Planck constant and the speed of light. So wavelength effectively is inversely proportional to energy. Now, visible light does not have enough energy to remove electrons from molecules. Visible light is split by wavelength into color that we perceive, starting at blue, purple, down to lower ends of the spectrum, below 500 nanometers, up to red at higher up to sort of 650 nanometers. Visible light is quite special as it's able to get through the atmosphere. It has enough energy to drive reactions such as photosynthesis, but not too much energy to cause harm. Thus, there's a reason that a lot of life has evolved to visualize it. Remember that electrons occupy discrete pockets or shells and subshells around a central atom. I think I always remember my A-level chemistry textbook pointing out that an atom is the size of a pea in the center of Wembley Stadium, and the electrons are around the edge of the stadium. Well, photons can interact with these electrons, specifically the electrons in the outer shell, which are freer and so more able to move. And I've drawn this in a diagram. These straight lines are just these circular lines drawn out in a straight way. And this sort of funny line here is a photon coming and interacting with the electron. This then gives the electron energy, which allows it to move into a different shell or subshell here, and it will then at a later time fall back down to its original shell. This is how ionizing radiation is more dangerous, because it will give the electron more energy that will allow it to come completely off from the atom and not be associated with the atom any longer. But when visible light hits, the most important feature is that the difference in energy to get from this shell to this shell is a particular value. It's a quantifiable specific value. The electron can't get somewhere in between these two shells. It has to move to particular shells. And if we remember that, and I guess the other thing to say is that this difference in energy level is the exact energy of the photon that hits it will be absorbed, allowing it to move that exact amount. Thus, only a photon of specific energy can actually produce this movement. And if we remember the equation E equals hc over lambda, we know it will be one specific wavelength of visible light. And thus, if you place a gas of the same atoms in a tube and pass light through, you'll get something that looks like this. This is an absorption spectrum. The black lines correspond to photons or a particular wavelength of light where the light has not been able to pass through the gas because it corresponds to these particular change in energy levels, and electrons will move from one energy level to another, meaning that the photon has not got through to your detector at the back. And each different atom will have different energy levels and electrons that are freely able to move. So absorption spectra will look different with different atoms. And this is an important feature that we'll come on to in the photometric lecture series. The color of this gas will be the complementary colors of these two wavelengths of light, or that amalgamation of the colors of these two, the complementary colors of these two absorbed wavelengths. And so just to finish off, I just want to sort of give a quick way of thinking about methods to apply to each of the lectures starting next week, just to sort of conclude. So all analytical methods are about separating your analyte of interest from the sample so that you can describe it, either quantifying it or saying whether it's present or not. There are not that many different methods, but there are loads of analytes. So think about the following for each analyte. What is the method required to identify the particular analyte? What do I need to do to prepare the sample to place it on the method? This starts at the pre-analytical factors, such as using the correct tube type, deciding whether you need to centrifuge the sample, handling it correctly, but it also extends into the preparation steps that may be part of the method. And once separated on the method, how do you actually quantify the analyte? How do you produce a signal that can offer a meaningful result and be compared to other results? But in conclusion, we've talked about sensitivity and specificity, how they describe errors associated with qualitative tests, but we've been very specific that we need to be aware of prevalence when using these. Biological variation consists of within individual components, CVI, and a between individual component, CVG. Knowledge of biological variation allows you to define reference intervals, but be cautious when applying these clinically. And analytical chemistry is about separation of your analyte from the sample and then quantifying it.